Now we are going to discuss about metric tensor. Now let us consider a rectangular coordinate system. The coordinates are x, y, z. Now the square of the distance between any 2 points is expressed by dx square is equal to x2 minus x1 whole square plus y2 minus y1 whole square plus z2 minus z1 whole square. Now x2 minus x1, the difference, this is a differential coordinate dx square and dy square plus dz square. So this you are choosing 2 points A, B, and the distance between these 2 points is you call as a ds, and the coordinates of the point A is x1, y1 is z1, the coordinate of the point B is x2, y2, z2, and the distance ds is given by this expression. Now if you express the coordinate x is equal to x1 coordinate, y is x2 coordinate, and z is x3 coordinate. So we are using the superscript to represent the coordinates x1, x2, x3. Then this becomes dx, the ds square. Actually, this is a ds square is equal to dx1 whole square plus dx2 whole square plus dx3 whole square. So this is for a rectangular coordinate system. In general, you can write down this is called as a line element. This is a line element. We are calling this a line element. ds square may be expressed as gij, dxi, and dxj. So we are so this is for a particular coordinate system we are writing a rectangular coordinate system. Now this is for in general you can write this is the expression. So this is a 3-dimensional Euclidean space in which gij are independent of coordinates. So here g11. So here the I runs from 1 to 3 for this 3-dimensional system. I runs from 1 to 3 and j runs from 1 to 3, and once if you perform the summation, the first term is g11 dx1 whole square. So g11 will be 1. So this is 1. Similarly g12 is 0, g13 is 0. Similarly if you perform the summation, g22 is 1. So here this is g22 is 1, g33 is 1. For all other values are 0. So this is 1, 1, 1 for all other values are 0. So you can write down dx here, dx2 here, dx3 here, and dx1 here. So dx1, dx2 can be arranged in the form of a row and as well as a column, and the coefficient can be filled here, and this is your gij values 1, 0, 0, 0, 1, 0, 0, 1, 1. So this is your gij values. Now this is for a 3-dimensional rectangular coordinate system. Now if you choose a spherical coordinate system, in spherical coordinate system the coordinate first coordinate is r, x2 coordinate is theta, x3 coordinate is phi. So in this coordinate system ds square is equal to dr square plus r square d theta square plus r square sin square theta d phi square. So the coefficients are g11 is 1, g22 is r square, g33 is r square sin square theta. For all other coefficients are 0. So off diagonal elements are 0. Now if in a 3-dimensional Riemannian space, this coefficient g11, these values are dependent on coordinates. So here in the previous case, in the Euclidean system, g11, g22, g33 are just 1 1 1. So this is independent coordinates, whereas in Riemannian space the coefficients are g11 is 1, g22 is r square, so this is a function of coordinate. Here r square sin g33 is r square sin square phi, so this is a function of coordinate r and phi. So if the g and the components g I j are dependent on coordinates, then that space we call as a Riemannian space. So this is a Riemannian space. So in general, let us write let us choose n-dimensional space. In the n-dimensional space, the line element is expressed as ds square is equal to gij dij dxj. So this is your expression. Here I runs from 1 to n, j also runs from 1 to n. So this component gij is called as a metric tensor. So this tensor we call as a metric tensor. Actually this is a again 2 dimension. So for n dimension the rank is 2. If it is a rank, gij is a tensor of rank 2. If it is a rank 2, this can be expressed, the components can be expressed in terms of the matrix form. If it is a tensor of rank 1, the components are can be expressed in terms of the vector. So for rank 1 it is a vector. For rank 2, then the tensor is a matrix. So here is a tensor. This is a symmetric tensor. So if you note down the gij values for here for Riemannian space as well as Euclidean space, you will find that both the matrices are symmetric. So this is a symmetric tensor. Now let us discuss about conjugate or reciprocal tensors. Now we are having the components of the tensor gij. This is a matrix form. gij is also because since it is a rank 2, it is a matrix. So now let us write down the determinant. The determinant of gij we call as g. So g denote the determinant, the elements jij in which we assume g is not 0. So the determinant should not be 0. So it should not be 0. That is important. If it is 0, then we cannot find the gij. So the gij and the contravariant components can be is possible only for tensor whose determinant g must be non-zero value. Now let us define the contravariant tensor gij. This is a rank 2 contravariant tensor. This is defined by gij is equal to cofactor of gij by g. This is a determinant g and this is a cofactor. Now gij is a symmetric contravariant tensor of rank 2. Once if the tensor covariant tensor is a symmetric, then the contravariant tensor is also symmetric. So the reciprocal tensor is also a symmetric. And this reciprocal tensor we call as a conjugate tensor. Now let us discuss. Now let us take write down the components of the covariant tensor gij in the matrix form. This is g11, g12, g13. So they are arranged in the row. g21, g22, g23, the second row. g31, g32, g32. So these are all the components are arranged in the form of the matrix. Now it can be shown that so this is from matrix theory it is possible to obtain this result. If you take a gij, so any one element in the ith row and multiplied with its covariant matrix. This is um, g of I comma j. This is a cofactor of this element. If you choose g I ij, this is the ijth element of a matrix. You choose and find its cofactor gij. So this is called as a cofactor. And if you perform the summation over j alone, so j you j. So I is for example, we choose I is equal to 1. So the first row, one suppose j may be j runs from 1 to 3 for a 3 by 3 matrix. So suppose if we choose I is equal to 1, g11 g of 1 comma 1 means the element g11 is the element in the G matrix, and find its cofactor and plus here, since j runs from 1 to 3, the next term is g12 g of, suppose for example you can write down, if you choose I is equal to 1, g11 g of 1 comma 1 plus g12 g of 1 comma 2 plus g13 g of 1 comma 3. That is equal to, you will get the value of the determinant. So this is true for any other element also. So instead of choosing I is equal to 1, if you choose I is equal to 2, again you will get the expression, you will get G. Or if you choose I is equal to 3, you can write down this expression, then you can get the value of the determinant. So from matrix theory, you know that Gij, one the element in the matrix, and G of I, you multiply with its cofactor and they perform the summation over G. Now here Gij is the cofactor of Gij. There is a summation over J only, that is important, because we already mentioned that whenever two indices are repeated, there is a summation over J. But here I am explicitly mentioning that there is a summation over only J, and I is a free index. J, there is a summation over only J. So we are not applying Einstein summation convention for the index side. So you have to perform only, the summation is only through from j is equal to 1 to n. So here it is 1 to 3. So that is important. Summation over j is, you have to perform the summation only to j is equal to 1 to 3 in this case. Also it can be shown that Gij, Gpj, suppose this is a ijth element in that matrix, this is the ijth component, and if we take the cofactor of pjth element, this is when I and p are, so here this is not equal, when I and p are not equal, then only this is true, which is important. I is not equal to p. If I is equal to p, you will get the value of the determinant. If it is different, then this must be 0. So this is so we have to take these two. So here Gij, G of I comma j is equal to G. So this is when I, this I must be same. When here it is I, this is p, these are different. If it is different, this value must be 0. So this is important. Now let us take a simple example. Now let us prove the covariant metric tensor Gij multiplied with the contravariant vector Gpj to make a product. And if you make a product, and this becomes delta Pj. So there is there is a summation over j, so actually this will be delta pi. So if you perform the summation over j, this is delta p. So only when p is equal to I, you will have a non-vanishing value, otherwise it is 0. Now let us find the solution. Now you take g ij, this is a contravariant tensor of rank 2. By the definition, this is equal to cofactor of gij divided by g. We have already, from the matrix theory, we have already shown that gij is equal to cofactor gij by g. So this from the theory of determinant, we know that the gij element is the cofactor gij by the determinant g. This gij we call as the cofactor. So this is a given. Now gij is the cofactor of gij. So this is the cofactor of gij in the determinant. Now, so we know that gij, the covariant tensor of rank 2 into its cofactor. If you multiply these two, you will get the g. From this, if you take the g in the denominator, you will gij into capital Gi comma j. This is the cofactor by g. This is equal to 1. But what is this? Gij. What is this? Is equal to cofactor by the determinant. So this is called as the cofactor by the determinant. So this is cofactor divided by the determinant. So this expression. So that can be replaced by gpj. So gij into gpj, which is equal to 0 if p is different from I. So if p is equal to I, p is equal to I, this is equal to 1. If p is not equal to I, again this is 0. So in general, this is delta by, this is a Kronecker delta pi. When p is equal to I, it is 1. And p is different from I, this. So this can be easily proved. So this is a contravariant metric tensor of rank 2. This is a covariant metric tensor of rank 2. So the product gij gpj is equal to delta pi. So this result will be often used. Now let us consider this example. Now let us prove that the gij is a symmetric contravariant tensor of rank. This is a symmetric contravariant tensor of rank. gij, this is a covariant symmetric tensor which is given, and this is gij is a cofactor. Cofactor is also symmetric. So this gij is equal to contravariant tensor, which is equal to gij divided by g, is also symmetric. So since this is symmetric, this is just a number, so this is also a symmetric. Now if you choose a tensor Bm, this is a contravariant vector of rank 1, this is arbitrary contravariant rank, and the covariant rank can be obtained by, you multiply by Gmn, the symmetric metric tensor, covariant metric tensor, and if you make a product with Bm, then you will, so this is also this is a contravariant vector, and if you multiply, you will get Bm. So the index can be lowered by this process. So the lowering or raising of the index may be done by multiplying proper the symmetric tensor or symmetric metric tensor. Now let us consider this is a contravariant vector dm. You multiply it with a covariant metric tensor, the index may be lower, so will get dm. Now you multiply by the contravariant tensor of rank 2 gln on both sides, so you will get gln is multiplied. Here you write first gln and this gmn, because you substitute for bn from the previous equation, you will get this equation. Now this result gln and gmn, so the contravariant metric tensor and the covariant metric tensor gmn. If you make a product, this becomes a Kronecker delta, because there is a summation over n. Finally, we will get the delta Lm. So this you will get a Kronecker delta, and this is a non-vanishing value only when L is equal to M. So the index becomes L. So BL. So you will get the contravariant tensor. If Bn is an arbitrary vector, gln is a contravariant tensor of rank 2. By the quotient law, the tensor Gij is called the conjugate metric tensor. So if you multiply, suppose if you choose a arbitrary vector and if you multiply with any entity, and if the result gives the tensor, then the entity must be a tensor. That is quotient law. So if you take any arbitrary tensor and if you multiply with any entity, and after making the product, the result gives the again a tensor, then the entity must be a tensor. Therefore gln, so this must be a tensor. So in general Gij is called as a conjugate metric tensor. Now there is a simple problem. Let us do this problem. Find the g and the Gij corresponding to this line element dx square is equal to 3 dx1 square and 2 dx2 square, 4 dx3 square and minus 6 dx1 dx3. Now let us express so in general ds square is equal to Gij dxi dx. So this is the general expression for the line element. Now this is here there are I runs from 1 to 3 and j runs from 1 to 3. So in terms of the matrix Gij, the coefficient of dx square is here 3, coefficient of dx square is 2, and coefficient of dx3 square is 4. So this will be in the diagonal, because you can arrange dx1 here, dx1, dx2, dx3. Actually dx1, dx2 and dx3, and here column wise also dx1 and dx2 and dx3, and if you multiply dx1 into dx1 dx1 square, and the coefficient is written here, dx2 into dx2 square, the coefficient is written here. So like that you can write. Now the minus 6 dx1 dx2 can be split into two factors, minus 3 dx1 dx3, minus 3 dx3 dx1. Therefore, since it is a symmetric matrix, this coefficient minus 6 is divided into two parts. One is a minus 3 and here another minus 3 is here. So this is your Gi. This is your matrix Gi. So G11 is 3, G12 is 3, 2, and G33 is 4, G13 is equal to G31 is equal to max, because since it is a symmetric tensor, these components are the coefficients are like this. And the components G23, G32, they are 0, because there is no expression. dx2, dx3 is not present, dx1, dx2 term is not present in the line element, so they are 0. Now let us evaluate the determinant. If you evaluate the determinant, the value of the determinant is found to be 6. Now let us first find the cofactors of Gij of the element Gij. So now let us find for the element Gij, the coefficient Gij. Let us find the cofactor. This cofactor G11. So put I is equal to 1, J is equal to 1 in that matrix. You will find G11 is equal to 8. So actual cofactor is obtained by finding the minor and use the coefficient is expressed by -1 whole power I plus j. So evaluate the minor for each coefficient, and the sign must be -1 whole power I plus j. So using this you can find that the cofactor G11 is 8, G12 is 0, G13 is 6, G21 is 0, G22 is 3, and G23 is 0. So this can be easily obtained just by inspection from the matrix. You can avoid all this coefficient. And now using this definition, the Gij, the contravariant component, is expressed by the cofactor divided by the determinant. So the contravariant component can be evaluated easily. What is G11? G11 means we substitute I is equal to 1, G is equal to, so G, the cofactor G11 divided by G. So this is already G11 is 8 and determinant G is 6, so 8 by 6, so this is 4 by 3. So G12 is 0, so you can evaluate G13, G23, G22 is 1 by 2, G23 is 0, G31 is 6, G32 is 0, and G33 is 1. So from this value you can calculate these values. Now you substitute this value, the Gij, so in the form of a matrix. Contravariant components can be expressed by G1 is 4 by 3, which is given, and G13 is 1, alright. Then G22 is 1 by 2. Then G31, actually here G31 is 5 by 6. This is so once we evaluate, this is by 6. So you substitute Gij values here. You already know G, the covariant components, that is also given. This is given. The contravariant components we have now evaluated. If you multiply these two, if you multiply this matrix and this matrix, if you both, then the result will be you take the two matrix and the components are already evaluated. If you multiply, you will get a unit matrix. So one matrix is the inverse of the other matrix. So contravariant symmetric metric tensor is the inverse of the covariant metric tensor of the covariant metric tensor. So one is the inverse of the other. Now let us define what is associate tensor. Now let AI, the contravariant vector I, be an arbitrary contravariant vector. The inner product of AI with a covariant metric tensor. This is a covariant metric tensor. This is a contravariant tensor, and the inner product is denoted by. Suppose if you take a contravariant tensor and if you multiply with the covariant metric tensor, and if you make one index in the covariant tensor I is made to the index in the contravariant vector, then you will get the covariant vector. So the I will be removed and the lower index will be here. So this is called actually a lowering of index. If you want to lower the index, you take a contravariant vector multiply with the covariant metric tensor, and one index in the covariant vector must be made equal to the one index in the contravariant vector. Okay. Then we will get the covariant component. So covariant component can be obtained from the contravariant component by multiplying the covariant metric tensor. Suppose if you want to raise the index, then the contravariant vector, take the contravariant vector, you multiply with the you take the covariant vector, you multiply with the contravariant metric tensor, and if one index is made equal, then you, the result gives the contravariant metric tensor. So using the metric tensor of proper type, the index may be lowered or raised. So now this AI and AJ are thought of the contravariant and covariant components of the same vector. That is important. So for the same vector, because once if you get the AI, you multiply with GIJ, you will get AJ. So AI is the contravariant component, AJ is the covariant component of the same vector. So the contravariant component, the covariant component of the same vector can be obtained through this process. So once again, taking the inner product of both sides of the above equation, with the contravariant metric tensor G, JK we find. So if we take AJ, if you multiply the covariant vector, if you multiply the G, JK, and this AJ we have already determined AI, GIJ. We substitute for AI, GIJ for AJ, and this A, GI, J, GJK. So this you take the product, and this is a delta Ki. So this becomes a delta Ki. We have already shown previously that if you multiply one contravariant vector and one covariant metric tensor, and the result gives delta Ki. When K is equal to I, it is unity, otherwise it is 0. Now this you will have a non-vanishing value only when K is equal to I. So this right hand side becomes AK. This will have a non-vanishing. So here Gij, Gjk is delta Ki. So we are using this property and we will. So the relation between AJ and AI is reciprocal. So you are from AJ to AI can be generated through by multiplying the contravariant metric tensor. From contravariant vector to covariant vector, you can obtain by multiplying the covariant metric tensor. So AI and AJ are reciprocal. Therefore, this AI and AJ, these tensors are called as the associate tensors. The tensors are obtained as a result of raising or lowering operations with the metric tensors are called associate tensors. Now let us discuss about the raising and lowering of indices. Now let Aij be a contravariant tensor of rank 2. So this is on taking the scalar product of Aij with the metric tensor Gij. G. Now so if you multiply this one, now this J is a dummy index, so if you perform the summation, finally you will get a mixed tensor Aik, contravariant rank 1 and covariant rank. And again if you multiply with GIL on the index I and I, one index in the contravariant rank and covariant rank in the GI. So this is made equal, then there is a summation over I, so the final result will be, you substitute for AIK, AIJ, GJK. Now this is equal to AK. Once if you perform the summation over J, as well as you perform the summation over I, the IJ will disappear finally, and the tensor will be K. So contravariant tensor IJ to covariant tensor of KL. So by the process of raising or lowering, you can convert a contravariant tensor of rank to covariant of the same rank by multiplying the contravariant metric tensor or covariant metric tensor. So this components Aij, this is a contravariant tensor of rank 2, and this is a mixed tensor, contravariant rank 1, this is the index I, this is covariant rank 1 Ik, this is covariant tensor of rank 2. So they all are obtained by proper multiplication of the metric tensor. So they all are the associate to each other. So they are all the associate tensors. Now there is a simple problem. Now if you take given K, one contravariant rank, ALM is a contravariant tensor of rank 2, BLM is another contravariant tensor. Now show that ALM contravariant tensor and the BLM covariant tensor of rank 2. If you multiply, the result will be the covariant tensor of ALM into contravariant BL. So now you here this index is the superscript LM. Here now it is another. So this is a contravariant tensor. This is a covariant tensor. This is a BLM is a covariant tensor on the left hand side. Here BLM is the contravariant metric tensor of rank 2. So this can be shown. So in order to prove this one, you consider ALM. This is equal to you take a covariant metric tensor APQ. And if you multiply by GPL, so one index P and one index P here, and the metric tensor, then that will be removed, and Q. So if you perform the summation here, this Q and Q, finally, since it's a dummy index, Q will be removed after summation. P also will be removed after summation, and you will get finally L. So the superscript, so the contravariant index alone will be present, AL. Similarly here, BL. If you choose B, the contravariant tensor, and if you multiply by the covariant metric tensor, so here the index R and R is made equal, and S is made equal. If it is so, then finally you will get covariant metric tensor. So now taking the inner product of the respective sides. So if you multiply ALM and BLM from the above equation, and you substitute for ALM from here, so this is you write this expression. From here you write down this expression, and write down the remaining part, GPL, GRS, GQM, GSM, and you group like this because you can interchange. So you can group. Now this is GPL, and here GRL. So here the L and L are made equal. So this becomes delta PR. So this is a delta PR. L will disappear because of summation. Here M, this index and this is identical. So it will disappear. So Q and S. So this is a delta QS. So this we will have a non-vanishing value only when P is equal to R and Q is equal to S. Therefore, in this tensor component, you have to replace P is equal to R and Q is equal to X. Finally, we will get A, P, Q, B, Q, P, Q. So we will get finally this result. Now here again, P is a dummy index. So any dummy index can be replaced by any index. For convenience, you replace P by M and Q by M. So this is ALM, BL. So we will get this result. Because the dummy index can be replaced by any index, P can be replaced by L and Q can be replaced by L. We will get the desired result. Now take one more example. Show that L square is equal to GPQ. This is a contravariant metric tensor, and AQ. AP is a covariant vector and AQ is another covariant vector, so that this is invariant. So for this, first you take one vector AP, write down this vector and the bar system, so the related by the transformation. Say A alpha bar is equal to partial dx alpha bar by partial dxp into AP, and the covariant vector in the bar system and unbarred system is related by A beta bar is equal to partial dxq by dx beta bar. So by the definition of the covariant vector and the contravariant vector, you can write down. You make a product, say alpha bar, A beta bar, and the the transformation form can be write down here, and you write down the components at the end for convenience. So AP, AQ. So that can be written like this. The components can be expressed after the transformation. Now look at the transformation. This transformation. So this is a if you put when alpha is equal to beta, so the transformation, you put alpha is equal to beta, so the transformation becomes like this. So this becomes like this, alpha, and this is now if you again see, look at this transformation, and this is for Kronecker delta and QP, because there is summation over alpha, it will disappear. So this is a Kronecker delta QP. So therefore this expression A alpha bar and contravariant vector A alpha bar, covariant vector alpha bar, multiply, this expression becomes delta QP and AP AQ. So this is a non-vanishing value, only when Q is equal to P. So you can replace Q by P. So this becomes AP. So this is a contravariant vector A alpha bar in the bar system, and this is A alpha bar is a covariant vector in the bar system. If you multiply, that value will be same as the covariant vector in the unbarred system, and the covariant vector, contravariant vector in the unbarred system, and the covariant vector in the unbarred system. So if you multiply these two, this product in the unbarred system and the product in the barred system are equal. So that means this is invariant. So if you multiply the two vectors in the barred as well as the unbarred system, it gives the same value. Then so here you have APA. So this product and this product gives the same value. So it is invariant. So it will be, let us call this is equal to L square. So you put the L square is equal to AP, the contravariant vector, the covariant vector, and this contravariant vector may be expressed as G, PQ, AQ. So from this you can prove this L square. This is a constant. So since it is invariant, you can express L square is equal to in this form.